Hello, this is section 2.1. The title is Measuring Change. We saw in a previous section when we talked about lines that the slope of a line is a rate of change. It's the change in y divided by the change in x. In other words, it's the change in the output variable divided by the change in the input variable. And a rate of change is giving us a measure for how quickly the output is changing with respect to changes in the input variable. In this section, we're going to explore this idea a little bit further, and in particular, a very important concept called the average rate of change of a quantity with respect to another quantity is defined. So here's a typical example, just a computation for this. I want to compute the average rate of change of the function y equals capital F of t equals the square root of t plus 4 over the interval 0 to 5. So typically you'll be computing the average rate of change of a function over an interval. To do this, here's what we'll do. This is the average rate of change of the variable y, wrt, with respect to t. And what it is a difference quotient, like we saw the other day. I look at the change in my output variable, f of 5 minus f of 0. Okay, this computes sort of the ending position, okay, where the function is at the end of the interval at 5, minus where the function was at the beginning of the interval, or f of 0. So that's the change in y. The denominator of the difference quotient is the corresponding change in the independent variable, so 5 minus 0. This is a difference quotient. We spent time on the first in-class day computing these, and here it is again. All right, so to do this computation, I need to compute values of the function in the numerator. To get f of 5, I should plug in t equals 5. In other words, plug t equals 5 into the function. To get f of 0, we plug in t equals 0. So what does that look like? That'll be the square root of 5 plus 4. That's f of 5. And then minus the square root of 0 plus 4. All of that's divided by 5 minus 0. And now I just have some numbers to try to simplify or to evaluate further. The first term in the numerator is the square root of 9. Minus the second term in the numerator is the square root of 4. The denominator, 5 minus 0, is 5. These roots are easy enough to compute. Square root of 9 is 3. And then minus the square root of 4, which is 2, all over 5. And so the average rate of change of the function f over the interval 0 to 5 in this case turns out to be 1 over 5. All right, this 1 over 5, it's a number, okay? Typically, for an average rate of change, we get a number. And like I said a minute ago, it's telling us kind of how quickly the function is changing with respect to t over the interval 0 to 5. I can also think about this number geometrically in a different way. And I'll do that here on the front board. 1/5, or this average rate of change, is the slope of the secant line connecting or between a couple of points on the graph of the function. In this case, connecting 0, f of 0, right? This is the coordinate of the point on the graph where the t is 0. And then the other point in question here is 5, comma, f of 5. All right, I'll make a quick sketch of this. Again, just to highlight what the secant line is and where that 1/5 is coming in geometrically. I want to sketch the graph of my function. In this problem, I'm in the ty plane. My function is y equals the square root of t plus 4. And so I recognize this as a standard square root function, translated 4 units to the left. In other words, in the negative t direction. So 1, 2, 3, 4. Here's minus 4. Okay, that's the t-intercept. And then here's the graph of this square root function. The 1/5, that quantity that we just computed, it's an average rate of change, but again, it's the slope of a secant line connecting 2 points on this curve. The points that it connects are the points that I wrote, 0, f of 0, right here. Okay, when t is 0, here's the height. Okay, what's that? Square root of 4, so 2. The other point that I'm looking at on the curve is over here somewhere at 5, and then the corresponding height is f of 5. F of 5 we saw was 3. So with these 2 points on the curve, if I were to connect them with a line, right, it's kind of, the line is a bit hard to distinguish between the curve in this case, but the slope of this line is 1/5. Okay, this is a secant line for the graph. The graph has, if I pick any 2 points on the graph and connect them with a line, that line is a secant line. The slope of these secant lines will vary, okay, as I consider different secant lines. But for this particular one, the slope is equal to 1/5. For our next example, here it is on the other board. We have a more applied problem here. This is number 10 from section 2.1. We're given a table of values, and so we can think about this as a function represented numerically. Okay, the table shows cumulative number of confirmed cases of H5N1 avian influenza, in other words, the bird flu. You might remember when that occurred worldwide. It happened, we have some data here for various dates in 2006, and this is from the WHO, the World Health Organization. All right, so here's our table of values on January 5th. The number of cases was 144. On March 1st, the number of cases was 174, etc. What I'm supposed to do in part A of this problem is compute the average rate of change of the number of cases from March 1st to June 6th and interpret my result. Okay, I want to get a sense of how quickly the number of cases is changing with respect to time. Let me introduce some notation first. I'm going to think about time as being the variable t, and I'm going to measure time in days in this particular problem. I'll say a little bit more about that in a second. For the number of cases, I'm going to use the letter capital N, and that'll just be a whole number of cases. So in our solution here, the table defines a function, like I said. I'm going to call that function n of t. So this is the number of cases as a function of time. And like I pointed out, the time variable is in days. With the following assumption, now this is something that I'm choosing here. I'm going to choose t equals 1 to be January 1st of 2006. All right, so if t equals 1 is January 1st, January 5 in the table here is the t value 5. The problem asks me, right, to compute an average rate of change. And so like in the previous example, I want to look at a change in the output, okay, a change in the number of cases, divided by a change in the input. The input is time here. Now, I'm thinking about my number of cases, my output variable, as being a function of t. What I need to do in this problem is I need to figure out what the t values are for March 1st and June 6th, because those are the two dates that I care about for this particular question. So, how can we do that? Well, it's not that difficult to figure this out, right? If you had a calendar, you could just count the days and figure out what number, right, what day of the year March 1st is. But I'm going to set this up for us in a table so that maybe we can see the results a little bit better. All right, in one row I'll have T, and in the other row I'm going to write some days from the year. So T equals 1, we know corresponds to January 1st. 31, right, would be January 31. Let's see, 32 would be February 1. 2006 was not a leap year, and so February has 28 days. 31 plus 28 is 59. All right, and so 59 is February 28. 60 then is the T value for March 1st. March has 31 days. And so, what am I doing here? 31 plus 59 brings us up to 90, right? So out here at 90 is March 31. The 91st T value is April 1st. And if we keep going, April has 30 days. 90 plus 30 is 120. So this would be April 30th. Okay, I think we see where we're going. The T value of 121 is May 1st. If I'm running out of room here, May has 31 days. So a T value of 151 would be May 31st. The T value of 152 is June 1st. And then in this question, I need to get to June 6th. And so here's June 1, right? 2, 3, 4, 5, 6. And so 53, 54, 55, 56, 57. 157. The T value of 157 corresponds to June 6th. All right, so this last date out here is June 6th. So what does my average rate of change formula look like in this case? The problem asks me about March 1st and June 6th, right? The average rate of change in the number of cases between those two dates. So in our table, right, we figured out that March 1st is a T value of 60, and June 6th is a T value of 157. All right, with that in mind, the average rate of change that I'm looking for here is a difference quotient. All right, coming over to here, and it's going to be capital N of 157. Okay, the number of cases on June 6th minus N of 60, which is the number of cases on March 1st, divided by the change in time, the change in the independent variable, and so that's 157 minus 60. To actually get a number from this difference quotient, I should look at my table and identify the number of cases on these two dates. All right, N of 157 is the number of cases on June 6th, and so that's 225. And capital N of 60 is the number of cases on March 1st, and so that number, that output is 174. All right, I guess we're going to keep kind of going backwards here. This average rate of change is N of 157, so that's 225, minus N of 60, which is 174, all divided by 157 minus 60. We can figure out what these numbers equal. I did this in my notes. Here we're getting 51 divided by 97, which is approximately 0.5258. This question also asks me for an interpretation. And maybe for us, in this class, and in real life, the interpretation is kind of what matters here, okay? When we're doing an average rate of change, thinking about an average rate of change, the units are always output units, because that's the numerator, divided by input units, because the denominator is input. And so here, my output units are number of cases, my input units are days. And so this 0.5258 has units of cases per day. I'm going to jump to the front board here to write a sentence for the interpretation of this number, right? Trying to give us a sense of what that 0.53 roughly means in the context of the problem. It's an average rate of change, and so it's telling us how quickly the output is changing on average. So one interpretation for this answer might be the following. Write my sentence somewhat carefully here so that you can use this as a model for your work. From March 1st to June 6th, the number of cases of bird flu increased. I can tell that it increased because I got a positive rate of change. If I had gotten a negative rate of change, that would correspond to a decrease in the output variable. All right, but here we got a positive rate of change, so the number of cases of bird flu increased at an average rate of change, of approximately 0.53 cases per day. So over this time interval, right, the number of cases was growing at about half a case per day.